All right, so today we'll do the usual thing. So we'll start off with some of the homework. We mostly finished 2 sections, so we have a decent number of problems to look at. So let's first look at section 2.3. And start with the really basic one. Number 1. So the really basic one is we're doing tangent planes and linearization, which is the same thing. So in this one, you're basically given the information and just see if you remember the formula. And so remember the formula here is, and the only difference between linearization and tangent plane will be what we write on the left. So for the linearization, we'll write the function is about equal to, whereas if we get the tangent plane on the left, we just do z equals, or some new variable, which I'll do in a problem or two. And then remember the idea is the linearization of the tangent plane, or tangent set, if you want to be more general, is the value at that point we're looking at, so 7, and then the gradient gives us the coefficients of the vector. So I get something like that. As I said, about the only difference between this and tangent plane is on the left, if it was a tangent plane, we would write z equals. And then, I'm not sure I'll bother doing this in the quiz because I said that really is kind of silly now since we have calculators, but in this setup, it at least is not something you can use a calculator for because you're not giving all the information. So like that. So here's the basic idea, which is if we have the value at the point of the function and we have the gradient at the point, then we get the tangent set, or the linearization of the function, by letting the gradient be the coefficient and getting something like that. So there's the basic one. Any questions on this? One where we actually have to do the work. So here, instead of linearization, tangent plane. And as I said here, we make you do the work, although it's a fairly simple function. So as with the last one, we need the gradient, which is just the two partial derivatives. And as you can see, this one's a fairly simple one, so I'll just do the derivative with respect to x, although you will double check me. plug in value. And I think this is annoying. So it'll be minus 90 plus 54. Oh, plus. So 153. And same type of thing. Minus 1, minus 30, minus 54. So those you're definitely to see if those numbers are okay. And then we need, like the last one, we need the value at the point. So if I put in that's what I get. Let's see if that makes sense. So minus 3, minus 45, minus 54. Yeah, something like that. And now once we're here, now we're just like the last one. As I said, the only difference is now on the left, because we're looking for the tangent plane, we put z equals. I think the question also asked to estimate a point, but I'm not going to bother with that because, again, you would just plug in the value. So here are the kind of the full type of question. This is really the type of question you need to be able to do from this section. So pretty much that's it. They can make it more complicated. I think one of them has you take the derivative of secant, which in theory you should know. I don't think I'd give you on a quiz or a test, but you know that. So pretty much those are the ones from 2.3 I want to look at. So any other ones from 2.3 that you have questions on? No? Okay. So 2.4. And the start of 2.4 is similar to a couple of the other sections. The first 15 or so, I forget how many, are ones where you're asked to get what's the gradient of f divided by g if you know the gradient of f and the gradient of g. And as I study those types of things, in theory you should be able to do, but you're not going to have to do it for a quiz or test, so if you want, you can ignore them. In fact, I'm going to ignore them. So 20 is kind of one of the first ones where you actually go through the steps. And again, it's starting with kind of a basic one. So given the gradient at the point 1, 2 is given by that. And then in and let's find the derivative of f with respect to t, although at t equals 0. Little thing, which is since x and y are really just one variable, they're just in terms of t, it's not necessarily a partial derivative. You can write that as a regular df dt. So for this, the first thing we have to check is what? So before we actually use the formula, what do we need to be able to do this problem? Since we don't have full information. So what do we need to be true about this? So we are going to need the two derivatives, what's derivative of x and what's derivative of y. But since we're not given the function itself, what do we need to be true at t equals 0? Right, so we need that. If we plug in, we get the only point we know about. So if I put in t equals 0 into x, I get 1 as I need. And if I put 0 into y, I get 2. In some ways, on a quiz or a test, you don't have to worry about it, because if this isn't true, you wouldn't be able to do the problem, which is not something I want to come up on a quiz or a test. So, but in general, you would have to check. And then we would go now the derivative, and I'm going to now write it as df dt because it is just one variable. So the expanded chain rule. And so we plug in derivative of f with respect to x is the 6. What's the derivative of x? And then derivative of y. So you'll put in something there in a second. So the first one is 2e to the 2t, or the way I usually do it, e to the 2t times 2. And the derivative of the second is just itself. And then we plug in the t equals 0. And we get 2 for both. So we get 6. Okay, so this is from 2.4, the one that you need to know. So in some ways, like the last one, there's just this one main fact that you should know from the section. So any questions on this? Oh, okay, so problem 31. So I'm not saying this is the last one I'm going to do, so I'll get to do another one in a second. I'm asking, are there any on this particular question? So I'll come back to 31. Right, so that's the same thing. Right, so you can think this is pretty obviously the dot product of the gradient and the, not sure what you want to call it, but the partial derivatives of x and y. Any other questions? Okay. So let me look at part of 22. Okay, my notes, I think it's 23 actually. And I shortened it because in some ways I probably wouldn't give you one like this. And after we do it, I'll tell you why. So here they're saying, here's this. So the real problem in 23 is more, it's something like x squared, y squared, and then plus other terms. And they ask for the partial derivative of f with respect to s and t. So both of them. And so like the last one, again, we have the two parts, except now it really is partial. means we take the derivatives. So take the derivative of f, take the derivative of x with respect to t. Oops, and I lost the squared. And they asked just for this, but let's say s is equal to 1 and t is equal to 1. Just see how it works. So suppose I want to find the partial derivative of f with respect to t when s and t are both 1. And in this case, directly that doesn't come up because partial derivatives are just numbers. But what is x and y? Oh, so I took the derivative of x and y with respect to t. And so 4 is equal to 2. And so that would be minus 32 minus 1630, 64. Something like that. This one I just did in my head. So the other ones I partially did before, but so is that right? Oh, sorry. Allison, I missed your question. Thank you, Cyrus, for answering. So is that okay? Okay, so let me do one more of these, which is actually the one that I was asked about, and I was going to, so let me do 31. So here we have a plate where and I think officially it's in a disk, so it's a plate that has a finite length. And if we're at this point, then the rate of change of the temperature as we move a meter in the x direction is 3 degrees, and the rate of change of the temperature if we move one unit or 1 meter in the y direction is -1. And it says now find, so it continues, and let's really make it into a disk. So we'll come back to this, but this you might have seen in Calc 2 or somewhere else, which is this is the polar coordinates for x and y. So because this is a circular thing, it makes sense to use polar coordinates, which we'll talk about later. Then let's get one of the partial derivatives of t with respect to these two variables. And let's do, in my note I did with respect to r, so let's actually do the opposite. Let's do with respect to theta. Where r is in meters and theta is in radians. It says find, so let's find the derivative with respect to theta. So as with others, the last two, it's again the two-piece. Let's see if I can fit it. So obviously this is 3. Derivative of x with respect to theta is minus r sine theta, and then minus 1 times the derivative of y with respect to theta, which is cosine. So now if I put in r equals 4 and theta equals 3 pi over 4, we get something. So the first little thing here is, for you on a quiz or test, you can just plug it in and you'll get a decimal, and that is fine. But this is one of the angles you should know. What is both sine and cosine of pi over 4? Right, so the square root of 2 over 2. So 3 pi over 4 puts us in the second quadrant, which means now x is going to be negative, but y will still be positive. So our sine of theta, which is y, will be positive square root of 2. So we're going to get 3 times 4 times, oops, I lost a negative, sine, which is square root of 2 over 2. And cosine is negative, because it's the x, and since we're in the second quadrant, x is negative. And does that come out to anything nice? So minus 6 plus 2. Something like that. Yeah. And we have units. So here the units are what? Yeah. So any questions on this one? Negative. No. Oh, but I did forget. Well, if I specifically ask for, then yes. So if I say give the answer with units, if I don't say that, then I probably wouldn't take off. So a little thing is, I did kind of skip one little thing, which is comes up with Gwyneth's question, which is, what did I kind of skip here? Which we did in problem 1. Right, we didn't plug in to make sure it's okay, which is, so what I should have done at the beginning is plugged in r equals 4 and theta equals 3 pi over 4 to check that we get the x equals negative 2 square root of 2 and 2 square root of 2. So in that sense, we are using the point, but it's not really coming up explicitly because there are no x's and y's. Any other questions on this? Okay, so those are the ones I will look at in 2.4. Any other questions from 2.4 that you want to look at? 32. Give me a second. So it's doing kind of a similar thing. So it says gravitational electromagnetic forces are acting on a charged particle in space. Let F equals f of x, y, z be the magnitude of the net force which acts on the particle at that point in meters. Suppose at 132, the partial derivatives are given by this in newtons per meter. If the position of the particle is given by that, where t is in seconds, and what is the rate of change of the magnitude with respect to time? I started writing a partial, but again, since x, y, and z are all in terms of just one variable t, it's really a regular variable, so df dt. And it says at t equals 1. So I forgot to check this in the last one, so here the first check is make sure that if I plug t equals 1 in, I get the 132, and I do. Which means we can do the problem. Otherwise, we're not going to be using the 132. And so this one, I'm not going to write out the notation that derivative of f with respect to t is the derivative of f with respect to x times dx dt plus dot dot dot. Let's just put it out. So it'll be the 4.5, the derivative of x, because this is x, y, and z. And then plus the derivative with respect to y. And then derivative, oops, got ahead of myself. Derivative with respect to t, z. And then it's equals 1. I get something 9 plus 30 minus 2, so 37. And since the partials with respect to x, y, and z are in newtons per meters, and since the derivative of x, y, and z with respect to t are meters per second, we'll get back, that's supposed to be the newtons per second. since we're not in physics, I don't worry too much about the units. So any questions on this? Any others that you want to look at? Okay, so we did part of 2.5, pretty much all of it. Again, like the last couple sections, there isn't too much to it, but let me start with an example, because I think I missed one type of thing. You'll let me know if I did. So 2.5 is directional derivatives. So let me start with the function. Do the preliminary for most of these few sections, which is gradient. Pretty much in all the sections, we want to get all the partial derivatives. So what is the gradient of this thing? Oh, if. Sorry. So if the function is equal to that, then what is gradient? And so it is, again, just all the partial derivatives. So 10xy, and then comma 5x squared. You can see I made this fairly simple. And then the 6z squared. And if I put in 10, 1, 2, 1, I get 20 comma 5 comma 6. Because y is 2. So, okay, so I've been using that for a little while. And now the new part for the section is find the derivative in the direction of, let's say, 2, -2, 1. So first is the preliminary step. So I'm checking to make sure you remember what direction means, which is I say in the direction of this vector. But is that a direction? This has come up in the last couple classes. Is that a direction? No, because it needs to be a unit vector. So we need to get the length. And again, you can kind of see I made it nice. The length of this is 3. So therefore, the vector we care about, so the real direction is that. So the 1/3 times that. Because the you got used to the fact that we're doing square root. So the sum of the squares, which is 9, and then square root of that. So that's the preliminary. And now how do I get the directional derivative? Right, so the dot product. So we're going to do the 25, 6 dotted with the 1/3 to -2, 1, which is 40, 30, 12. And that says if there were units, so for example, suppose everything was in meters, that would say for every meter I move in that direction, F will increase by 12. Okay, so this is the new part where there's a follow-up. So let me remember the 25, 6. Okay, because the follow-up is going to be in which direction does F change as quickly as possible. So first, before I get to that, let me ask the setup. Any questions on A or B? Okay, so C. So in which direction does it increase as quickly as possible? And the related question, which we'll find, is what is the rate of change in that direction? So in which direction does it increase as quickly as possible? Right, so the direction of the gradient. And like the last part A, we just have to make it into a direction. So we look at the length. One over square root of 4. So like it much quicker than I am. And I'm going to do in the 2 steps because because in getting the length, I'm answering one of the 2 questions, which is that's the rate of change in the direction. And then the direction is the actual unit vector in the direction of the gradient. I'm not going to write it down, but if I ask in which direction does F decrease as quickly as possible, then what you just have to do to these 2 answers, oops, sorry about that. Right, just put a negative in front. So the rate of change in the direction that F decreases as fast as possible is negative square root of 461. And the direction is negative 1 over 461, 25, 6. So because of that, I probably wouldn't ask you for both. That's supposed to be a D. Not sure what it just did to me. Related question that also comes up is, and in some ways I'm cheating a little bit here with the language, but in which direction does the function not change at all? So in the boring direction, 0. But yeah, so in a direction that's perpendicular to the gradient at that point. And that means I need a vector that is whose dot product with the gradient is 0. And there are lots of ways of doing that. So for example, I could just make one of the terms 0. So I'm going to do that. So I'm going to say, well, let's make it 0. And then what can I put in for the other two numbers? Because for two numbers, it's pretty easy to get something that's perpendicular. Right, so switch the order of the other two numbers and make one of them the opposite sign. Because now notice 5 times 6 is 30, 5 times 6 is 30, they're going to cancel. So with 2, it's easy. Just flip the 2 and change one of the two signs. And Cyrus also is okay. You're making it so that we just get 1 each time, which is also, of course, okay. But as I said, they're now an infinite possible number because I did let first one be 0, but there's no reason it has to be 0. I can make the third one 0 and make it 1 comma negative 4 or whatever. And the only little thing is, as with the last one, I just need to make it into a direction. And the reason I'm kind of cheating with the language is I can only go in an infinitesimal distance in that direction if I want to keep constant, because if I keep going, it will now be at a different point, and therefore the gradient will have changed a little bit. So the direction I have to move to stay constant will again change. So I'm kind of cheating. Okay. So any questions on this? All right, so let me actually move on, because what I'm going to do today is similar to what we did yesterday, which is that after I do a little bit of the next section, I'll give out another little handout, give you the 15-20 minutes to try, and go from there. Yes, so that's all. So as I said, there are kind of an infinite number of possibilities. So I did 0, negative 5, 0, positive 6, negative 5 also works. So there are lots of possible directions. So any other questions on this? Okay. So 2.7. So this is looking at level sets and gradient vectors. And really, in some ways, the idea is in the last couple sections, we've gotten tangent lines and tangent planes for surfaces if they are defined explicitly. So that's something like z is equal to f of xy. Really, what we're doing in 2.7 is the same thing, except what happens if the function is now implicit. And we're kind of going through what we're going to call level sets. So remember, a level set, and let me actually just do with an example. If this is a function, remember a level set is what happens if I set the function equal to a particular point. So we get level sets by setting the function equal to a constant. So in this case, and I think I might have even done this paraboloid. My lovely circles. I have kind of three cases. If c is less than 0, I get nothing. If c is equal to 0, I just get 0.00. And if c is more than 0, I get a circle of radius squared of c. But notice what we're doing when we get these sets is, for example, if c is equal to 1, I get still a function, but now a function that's kind of implicitly of one variable in terms of another variable. As opposed to at the beginning, I have z is equal to x squared plus y squared. That's an explicit function of x and y in terms of x and y, whereas this, for example, could be an implicit function in terms of y. But with the implicit function, I can ask the same type of question, such as, what is the tangent line? And notice this is two-dimensional, which means I'm going to get a tangent line. Whereas if I ask what is the level set for the original one, z is equal to x squared plus y squared, I'd be getting a tangent plane because I have something that's three-dimensional. So by setting the function equal to a constant, I've lost a dimension, and so on. So looking at the level set, and this is c equals 1 and 2, if I'm going to draw the gradient at this point, what is that going to look like? And try not to do it explicitly, because obviously we could get the gradient and then plug in that point, which is 1, 0. But think about what we got from the last one. In which direction is the gradient going to be pointed? So first, let me make it exactly like the last one. If I'm at this point, then in which direction should I move for the function to increase it as quickly as possible? And that's in terms of the gradient. And so it should be obvious, although we should really do the work to show it, is gradients are going to be that's supposed to be the word orthogonal, is orthogonal to the level set. And so therefore, when we want to get the tangent whenever, we're going to use this idea. So this, as I said, sort of is coming from 2.5, where we're still using the fact that the gradient is in the direction that we're increasing most rapidly, which means it's going to be perpendicular or orthogonal to the level sets, because we want to move from one value to the bigger value as quickly as possible. So I go back to this, and again I have the f of xy. Start with the really simple one as usual. Let's find the tangent line. of the level set through, say, the point 1, 1. So notice that is telling us that really what we have here is our function is this. But as with the last few sections, our first step is to get the gradient. Oh, just plug it in. If you plug in x equals into here, if you plug in x equals 1 and y equals 1. And by level set, we're saying that f is fixed. So at 1, 1, we get f is equal to 2. And since we're looking at a level set, it's saying we're only looking at points where it's equal to that same value. So this part is what makes it so it's 2. Just looking at the time. So if I plug in, what is then the tangent line? So this is normal to the tangent line. I forget if we've done this or not. You'll tell me after I do it. So the idea is pretty much like a tangent anything, which is we use that to get the coefficients. And after I write this, you'll tell me if we've done this or not. I forget if we have. So pretty much the same way we get tangent of just a plane. Right? Once we have a normal, we write like that. And the only reason that this is a tangent line as opposed to a tangent plane is that it's 2 dimensions. Oh, so go back to, so here's our picture again. And imagine there are a bunch more circles. And imagine I am here. And remember, this represents 0 and then 1 and 2 and so on. I know from the 2.5 that if I'm at a point that the gradient will be the direction that the function increases as fast as possible. So if I want to go from where the function has a value of 1 to the function where the function has a value of 2, I want to go in the direction that's going to get there as quickly as possible. So I could go this direction, right? Or I could go this direction. But it should be pretty obvious that this is the quickest way. Right? That's the shortest distance. And therefore, it's the quickest way. And so this is, we're cheating a little bit, or I am at least, because it's not obvious that that is perpendicular. So here it looks like it should be. But if you start actually doing it, right, we have here is the gradient in general. If you start plugging in actual points, you can check to see that the gradient you get is actually perpendicular to the level set. For me, it's hard to show because my circles aren't very good. But if you draw it a bit nicer and then draw onto it the actual gradients at the different points, you'll see that, it really is perpendicular. But it really, the idea is we know the gradient is the direction that the function increases most rapidly as possible. And looking at the set, it does look like it should be perpendicular. So I'm being vague. Little thing is the first part of this section, a lot of it is just graph the level sets and then graph a bunch of gradients to see if it does look like they're perpendicular. Right, and then we again sort of know from the previous section that the tangent line is where it's just hitting. So there's the tangent line, and you can see they are that one. In fact, the tangent line is the direction where it doesn't change. Not really. The theory you should sort of have, but you don't have it complete. Okay, so here's one idea. Let me do another example. And I'm going to do it in two different ways to show that this section and one of the previous sections really are the same thing. So let's find, oh, so, right, so the first one, Yang, the first thing you do is a tangent line because there are two dimensions, x and y, which means it is a one-dimensional object. What we could solve for y in terms of x. The second one you're actually missing. The second one would also be a tangent line, but our usual thing is we usually do z is equal to 2 plus 2x minus 1 plus 2y minus 1. In case now we have added a third dimension, and so now it's a tangent plane. Right. So I can't write on your thing, but in your second one where you do 2 plus 2x minus 1 plus 2 minus 2y minus 1, if you set that equal to z, then that is now a tangent, that is now a plane. In some ways, that's what we're going to see here. So here, let's do it the way this new section is doing, which is the new section is saying, well, this is making it implicit because at 1, 2, negative 1, the function is equal to 15. I think. Let me just double check for a second. So 6, 14, 15, yeah, is 15. And we get the gradient. So let's see if it's 17. Okay. So the new way is we take the gradient, 15 here, so it's kind of a bad thing that there are two 15s, but this 15 doesn't really come in. And we get the, using the point, we get that. And that last thing is z plus 1. So the idea is this is our normal vector. This is the point on the plane. We just use the method from chapter 1. Between those two, we have a normal vector, we have a point on the plane, we get the equation of the plane. On the other hand, we have put in the 1, 2, negative 1. Say it's a level set. It says really what we have is this. And here, since I've made it nice, I can make it look like a previous section. z is equal to a function of x and y. And so from our previous section, we had it in this form. So in this form, we have a z as a function of x and y implicitly. So we do it one way. Here we can actually get it explicitly in terms of x and y and use the and so we get the gradient in terms of z which is of course the same as what we have above, except without the last variable. And we know that z at the point 1, 2 is supposed to be just a comma there, 1, 2, comma, negative. If you read it, z at 1, 2 is equal to negative 1. So we can get the tangent plane like we did in 2.3. And it's equal to the negative 1 plus 20x minus 1 plus 15y minus 2. So we had this method from 2.3 if we have z explicitly in terms of x and y. In this one, once we put in the point and say it's a level set, which means we're fixing it equal to a constant, we have now z implicitly in terms of x and y, and we use this slight variation to get the tangent plane in that case. But if you look at those two, pretty obviously those two equations are the same. It's just that this second way of doing things, this way here, is a little bit nicer because we don't need to be able to solve for one of the variables explicitly in terms of the other. So it will always work, whereas the second form here, we need to be able to solve for one variable explicitly in terms of the others. And the only difference between tangent lines and tangent planes and tangent sets is how many variables there are. So if when you've written it, there are 3 variables, like the 2 equations we have here, it's a tangent plane. If there are 2, then it's a tangent line. And if it's more than 3, we generalize and call it a tangent set, because it could be 4-dimensional or 5-dimensional or whatever. So in some ways, what we're doing in 2.7 is saying, well, what happens if we have a function that is set equal to a constant, which is what we're doing when we look at a level set, which means that we have a function that is implicitly in terms of the other variables, but not explicit. So any questions on this? So as I did yesterday, let's try again. I'll share something, give you the 15-20 minutes to try, and then we'll go over it. Assuming I get it. So there we go. So pretty much what we just did is just have you try it instead. So I'm going to so Keenan, no. It's just that if you can't solve for one of the variables explicitly in terms of the other one, then obviously you can't use that second way I did things. And Gwyneth, since we have mostly finished these, the sections on the quiz will be 2.1, 2.3, 2.5, and 2.7, which seems like a lot, but as we saw from the last problem, some of the stuff in 2.3 and 2.7 really are similar. It's just how the function is expressed. So pretty much, if you look at, oh, actually, it was 2, 4, and then I'm missing 2, 4. Oh, 2, 4, right? So 2, 4 is the chain rule. So obviously not all of it, because the quiz itself will be take 20 to 30 minutes, but subset from it. I'm not sure. So when I looked this morning, some of them had been graded and put up, and some had not. So for if you did not submit it through Blackboard, then I graded it, and I put those grades up this morning also. But last I looked, the TA, it looks like he graded about half of them. So I'm not sure what that means. So sorry about that. I forgot to mention that. So your quiz grade might have been posted. A little thing, which I should have done, is if you submit it through Blackboard, your corrected version should be on Blackboard. If you just email it to me and did not submit it through Blackboard, then it won't be there. And so if you want to see it, send me an email and I can send you my corrected version. Okay. Otherwise, I'm going to say nothing for 10 minutes unless you have questions about these. Oh. So the quiz is actually a lot of material. 2.1, 2.3, 2.4, 2.5, and 2.7. So as I'm putting together the review for tomorrow, I'll probably drop off some of that because that's an awful lot of material. I'll write that down once we go over this. So for now, for the next 10, 15 minutes, just work on this. When we come back, and once we go over the answers, we can talk about the quiz and the previous quiz. Oh, sorry, I should have said. Besides having it here on, I also have this file in Blackboard under course material. So if you want to download it. Okay, so let's, I always like, yeah, this is kind of late, so kind of compressing here. So for problem one, so let's start with the actual numbers, and then I'll just fill in the derivative. What is the vector you get here? Okay. And what else do I need to do part B? So I need the gradient vector, which is right there. I also need the point. So if I put in 1, 2, what do I get? 7. Okay. So therefore, Z is equal to, and so notice this is not from the one we just did. Right, so whichever order you want to do it. Oops. So let me bring down gradient. All right, so as the one we did today, the first thing we need to get is the unit vector in the direction we want. So what is the length of this vector? Oops. So therefore 1 over 13. And what do you get? Yep. And now what is the tangent line at the point 1, 2? Yeah, pretty much all the information we need. So it's kind of a subset almost of what your answer in B is. So what is the tangent line to the level set? Yeah. Okay, so any questions on these? As I said, after class, I'll write them up and put them on Blackboard, but any questions on these steps? Because it seems when I move to the next page, it erases stuff. So any questions on any of this? Okay. So this we just did also. In which direction should we move so the height decrease as fast as possible? So of course, our first step is we're going to need to get the gradient. And again, let me start with the actual numbers. Does this come out to anything nice? Negative 0.04, negative 0.08. Someone else get the same thing? Yep. Okay. So now we just need, this I assume is not, actually it might be okay. What is the length of that thing? Or, yeah, square root of 80 over, well, I'll do it this way. Since getting too slight late for numbers. So I can bring out the 0.01 outside the square root, and 4 squared plus 8 squared is square root of 80. So something like square root of 80 over 100. That doesn't sound right, but something like that. So that's the rate. What are the units of that thing? Oh, right. I lost the negative. In the increasing, it would not, but yes. And what are the units? So feet or foot, feet per foot. So it's kind of a confusing one because X and Y are both in feet. H is also in feet. So it says if I move 1 foot in this direction, my height's going to go up by that number of feet. And the direction is over this thing. And then since we're going the negative direction, it actually comes out nice. I get the 0.04 and 0.08. Okay. There are in the original. So if I'm moving in that direction, it's the negative, but here I want it to decrease, so I put a negative in front, so the negatives will cancel. Right? So this, without the square root in the front, is the direction in which it increases most rapidly, because that's the gradient. Right, so I could put a negative in front. So that's the direction in which it increases most rapidly. So if I put a negative in front of it, it'll be decreases most rapidly. And so what I'm doing to go from here to, so this is for increases. So therefore decreases will be equal to negative that same vector. And of course I can distribute the negative to make it positive. So either way you want to do it. On the quiz, I'll try to make it so the numbers come out a little bit nicer. These are not that great. So give me a direction that if I move in that direction, it will remain constant. Right. Right. So in some ways I was going to do the same thing. So I want something whose dot product with this is 0. So it's probably easiest. So I flip and then change one of the signs. But I might as well make them nicer numbers. So if you want to leave it as 0.08 and negative 0.04, that would be okay. But then you're dividing by a kind of a nasty thing. Also, there are 2 directions because I could also do -2 and +1. Okay. So that's one type of question. So let me leave it there for a second. Any question on either of these two? Oh, so inside the square. Oh, what's under the radical is, so thank you. So yes, that's 1 over square root of 5, just the length of the vector. Gwyneth, when you say flipped it in the gradient, not in the point, I'm not sure what you mean. Okay, good. I guess. All right, so let's do this last one. So this now really like the one we did today, which is just we get the gradient and let me do it this way again, since it's a fairly simple one. When you plug in the numbers, what do you get? Wait, negative. Well, but so -6 and what? Well, as you're writing it, let me write the. Okay, good. And therefore the tangent plane is this is kind of a pain to write, so I'll just write. So any questions on this? I don't need to know that because in this one, since we're looking at a level set, it doesn't come in. So notice that's the difference, and I'm not going to go back because I'll erase this stuff. But if I want to get the tangent set at the point 1, 2, -1, then I would need to get what is the function at that point, and then do it similar to the one on the previous page. I think part A, I forget which one it was. But here, since we're doing the level set, that's going to go away. Anything else? Okay. So, unlike yesterday, where I then did my usual quick end of something new, I'm just going to well, let me just make it a simple one. Oh, actually, I didn't know. I was wondering why it. Sorry about that. I was wondering why I was making it so thick. So, example. Really a simple one. So I make this into like a Calc 1, Calc 2 question, and then we'll stop and really do it tomorrow, which is if I want to find a local min or a local maximum, what do I do? Right, so I take the derivative, set it equal to 0. So I'd get the critical points. So here the equivalent would be I would take the two derivatives, set them both equal to 0. For here, this is a really simple case. We get something fairly straightforward. We just get x and y both have to be equal to 0. Once we get a possible point, what's one way of checking to see if this is a minimum or maximum? So how do I check, once I get a possible critical point, how do I check? So there are three ways with one variable. One way is to basically look at the graph, so plug it into the original function, see what's going on. Second way is with the first derivative test. Take the derivative, see if it changes sign, if it's going from positive to negative or positive. And then the third way, so it'll turn out that neither of those is going to be nice for us because graphing three-dimensional objects is kind of a pain. First derivative test is going to be kind of a pain. So what's the third way? Second derivative test. So we would take the second derivatives, and this one is nice. Both second derivatives are positive. So what do you think that tells us about the point? Right. Since those are positive, that means it's concave up, which means we probably have a minimum. Problem in more than one dimension is something weird can be going on. So for example, we could have one of these is positive and one is negative. It could be that these are both positive, but here it isn't. But the mixed derivative is really large, which means that between the x and y axis, as I'm moving around, it changes a lot. So it changes from being a maximum to being something in the middle. So the idea is I have a third possibility, which is instead of in one variable where you can have a min max or something else, which usually is an inflection point, but could just be undefined. For this one, it could be we could also getting a saddle point, which is it's a minimum in some direction, but a maximum in other directions. So the idea is going to be similar, just we're going to have to add some steps to deal with the fact that we can get saddle points. And we'll deal with that tomorrow. So let me stop here. The usual thing, I'll stick around if you have more specific questions. And two things. So first, quiz. So before people start leaving, let me what someone for. So the quiz will be on pretty much all of chapter 2. But when I'm writing up the review, what I might do is skip a little bit because that's a lot of material for a quiz. So you'll see more specifically tomorrow what's on the quiz. And then for tomorrow, look at the 2.5 and 2.7 homework. So now, if you're ready, I'll see you tomorrow. And if you have more specific questions, stick around. I'm going to stop recording.